warahmatullahi wabarakatuh. Here, Dr. Abdelaziz Rifai. Today we have a Hooke's law experiment. The purpose of this experiment is to find the K constant of the spring by elongating versus applied force. The apparatus of this experiment, we have helical spring, stand metric scale, and here the hanger is 50 gram, and different methods. So let us start experiments by filling the table. Here, we come here back here, this side. The equilibrium state, the original experiment position, here, we measure it. It is 9 centimeters. So here, we write it here, why not? Here, 9 centimeters is equal 0.09 meters. We convert it to meters. In this column, we have a mass, 0.05 kilogram. So if the hanger with 0.05 kilogram, put it here, we have the elongation. So the applied force here in the table, the applied force equal M multiplied by G. After that, we will have the actual metric stick reading. Now it is about 23 centimeters. So here, the actual stick, the metric stick reading, 23.23. The force is equal 0.05 multiplied by G is equal 0.49. So the displacement is equal the actual metric stick reading yi minus the original equilibrium state y naught, 0.09. So 0.23 minus 0.09 is equal 0.14. So we will add another mass, 20 gram, we add it to the hanger here. So like this, we have another elongation. The mass here, 70 gram. So it is 0.07 kilogram. The actual metric stick, you can read it here, 29 centimeters. 29 centimeters, so it is 0.29 centimeters. So here we have 0.07. The actual metric stick, we say that it is 0.29. The force weight is equal 0.07 multiplied by the gravitational G, 9.8, so it is equal approximately 0.69. The displacement is equal 0.29 minus 0.9, so it is 0.20. Also, so we will add another mass, 20 also, so it becomes 29, and so on. So here, we make it before, so the table will be like this. Here, the column is the force, and here is displacement, 0.13, 0.37, 0.43. He said that the graph applied force with spring, we make graph between the force and the displacement. He mentioned it here. He said that the displacement delta y in the horizontal axis. Delta y. So here delta y will be in the x-axis, and the vertical applied force in the y-axis. So here in the y-axis. Okay. After that, we will get K. He said that the spring constant K will be the slope. So the graph, right? The graph. That here the graph, the force, the units Newton versus displacement delta y with the m, the unit meters. So here in the y-axis, the force, and in the x-axis, the displacement. So the great problem is how to get the perfect scale. How to get the perfect scale. Look here, in the x-axis, to get the perfect scale, we should subtract the height value minus the lowest value. So 0.43 minus 0.14 and divided by the number of the masses. 1, 2, 3, 4, 5, 6. So 0.43 minus 0.14 divided by 6 is equal 0.16. So in the y, so here in the y-axis, in the axis is equal 0.05. Sorry, 0.43 minus 0.14 divided by 6 is equal 0.04. So we take it 0.05 meters. In the y-axis here, the force we subtract 1.47 the height minus 0.49 divided by 7. Divided by 7 is equal 0.16. So here 0.16 Newton. This axis 0.05 meter. So here, like this, the first here 0.049 with 0.14 with a 0.14. 0.14, as you see here, this is 0.05, 1. 0.015, 2, 0.2, 0.25, and so on. So here this is a 1. This is a 1. We need this axis 0.14. So here the 1, 3 divisions. After 1 with the 3 divisions. 0.49 in the y-axis. Here we have 0.48. So it is up of this value with the 1 division. So it is here. So this is the first point. The second point, 0.69 and 0.69 and 0.20. Is the x-axis 0.2 is here? This is 0.2. This is the 0.2. 0.69. It is up 0.4. It is up 0.64 by 3 divisions. So we write it here. The third point also 0.88 with 0.25. Here is 0.25. This is 0.25. 0.88. It is up 8 by 4 divisions. 4 divisions or 3 divisions. You know, because 3 multiplied by, if we multiply 3 by the scale, 0.16, it's become 0.48. 0.48 when we add it to 4, to this, to 0.8, to multiply 6, no, not 5, here, 1, 2, 3, 4, 5. 5 multiplied by 0.16, it has become 0.9. 0.9 when we add it to 0.8, it becomes 0.89. So it is near to this 0.88. Okay, so this is the third point. And so we complete the points. When we complete the points, we need to get the slope together, because the slope will represent the K constant of the spring. So here between these points, we have this point with this point. So we make triangle like this, and the slope, you know that the slope is equal y 1 y2 minus y1 over x2 minus x1. This is stop. This point here is 1.41 minus y1, this y1, if we see here, this can become 0.72 over x2 minus x1, x2 here, x2 0.4, because this 0.25, 0.4, minus x1 here, 0.2. So 0.4 minus 0.2, it's become 0.69 over 0.2, approximately 3.5, because it is 3.45. So it has become 3.5. 3.5, this is a slope. So K is equal 3.5 Newton per meter. So this is we can write it here. This is the value of K of the spring. This is the end.